Hello everyone, and welcome to Module 10 of INST728E on Network Analysis. This will be the final module of this course, and in this module we will look at how entities or people or organizations connect to each other in a network, and where these networks come from, how we can create these networks, and what we can do with them once we've done so. So first off, what is a network? So a network, or a graph, as it's also called, is a collection of nodes and edges, where a node can be your object or entity, like a user in social media, a hashtag, or a website, or a company, and an edge is a connection between nodes. So this connection can define some sort of relationship. In social media, it may be a follows relationship. In this case, B follows C, or maybe C follows B. Or in Facebook, it might be B and C are friends. In the World Wide Web, it may be the websites B and C are linked together because they're in the same domain or owned by the same company, or include hyperlinks to each other. So these kinds of graphs can represent many things, from links between websites to interactions between users. So maybe user A mentions user B in some post in social media, or A and B are friends in a social network. They could be co-stars in movies. If movie actor A starred in a movie with movie actor B, and movie actor B starred in a movie with actor C, what can we identify or learn from these networks? And they can also be co-occurrences between hashtags or URLs. So in a tweet, this may mean that hashtag A occurred in the same tweet as a link to a website B. And we could use this to characterize the kinds of people that share a particular website, or the kinds of topics that get shared on a particular website, or that link to a particular website. Now, some examples we can play with, or about which you may have heard, are things like the 6 Degrees of Kevin Bacon game. So in this game, you have Kevin Bacon, who is an actor who's been in Hollywood for several decades. And the idea for this game is to identify or name any actor you can think of, and then connect that actor to other actors based on movies in which two actors have starred. So for example, Tom Cruise starred in a movie Night and Day with Cameron Diaz, and then Tom Cruise starred in the movie A Few Good Men with Kevin Bacon. So the objective for the 6 Degrees of Kevin Bacon game is to find a path from any actor to Kevin Bacon. For instance, Denzel Washington played in a movie with Forrest Whitaker, who played in a movie with Kevin Bacon. So we would say in a graph like this, or a network like this, the actor Kevin Bacon has some really prominent or central role. That means that there is often a path from any given actor or any given node in your network to this central node, i.e. Kevin Bacon. So we say that Kevin Bacon has high centrality, where centrality is this property of being critical to the network, and people on the periphery of your network, or people that are not connected to very many others, you would say have low centrality. Now we'll use this idea of centrality to characterize networks and to identify authoritative users when we start to look at our own networks. But it's not just individual users that make up a network. A network can also be made up of groups or communities, where a community in general is defined by a collection of similar or highly connected nodes. So here, maybe B and C are a community, and A, D, and E are a community. And then you can have different communities that evolve, or communities that change over time, or communities can change based on the algorithm or the interpretation. So here we have A, D, and E as one community, and B and C as one community, but maybe A, D, and E are one community, and A, B, and C are another community. So the node represented by A may exist in both communities. So how do we identify communities? There are several algorithms for this. One is called Louvain. This came out of France. It's a very popular one. Graph partitioning. Another one is the Gervin-Newman algorithm. This is the one that we'll use, and there are many others. We won't go into exactly how these algorithms work, since this is an abbreviated course, but we can use them as tools, and what you need to know is that they take in some graph as input, and then return some collection of nodes that represent different communities in this graph. So now that we've talked about what is a graph, ways that we can interpret graphs, things that you can do with graphs, we'll now talk about the homework for Module 10. So the idea, as we've done before, is to fill out this notebook with information for your particular event, and then use the analysis that we're going to go through to find central users in your data, or who are the most authoritative accounts in the network of tweets referencing your particular disaster or event. Then once we've done that, run the community detection algorithm that we include to identify up to 5 of the largest communities. Now, there may not be 5, that's fine. And you can use these different communities and characterize them by their central accounts and common hashtags to figure out what those communities are built around, or what those communities most often share, or what is driving this communal influence. All right, so now we'll hop over to our notebook. So we'll open up the Module 10 notebook. And what we'll do with this notebook is go through some examples for building up graphs or building up networks, running some algorithms on these networks to identify central accounts, visualizing these networks to some degree, and then looking at the different communities that make up these networks. In terms of packages that we'll use, we have a bunch of packages that we've already seen, so NumPy and Matplotlib, etc. And we have NLTK for figuring out frequent hashtags. But the main new package that we'll include is this NetworkX package, which is a popular package in Python for doing network analysis. And then we have our event description, so update this to your event description. We'll run this, so since we're focusing on the Brussels transit attack. We'll read in the relevant tweets that we've been using for the past several modules. We have about 5,000 tweets here. And then now we actually get into building the graph. Now what we want to do here, we could just go through and add a bunch of nodes for all the users in our network, but that wouldn't give us information about connections. Now since we don't actually have the friends and follower lists for all of the users in our data set, what we do have are users that mention each other, or users that mention other users or other organizations. So we'll use those user mentions to create edges between our users. So we'll create what's called a directed graph. So there are different kinds of graphs. There are directed graphs that have direction in the edges. So edge A is connected to edge B, but maybe B is not connected to A. So in Twitter, this would be A follows B, but B doesn't follow A. This is in contrast to an undirected graph that you would see in Facebook, where if two nodes are connected, if I'm connected to a friend, then my friend is also connected to me, because in Facebook, friendship is bidirectional, whereas in Twitter, the friend and follower relationship is unidirectional. So we'll create this directed graph, and then for every tweet in our list of relevant tweets, we'll extract the username, make it lowercase, and then add that username to our graph here. Now once we've done that, we go to that tweet and pull out the user mentions, and for every mention, we pull out that screen name, or the screen name of the user who's being mentioned. Then we check to see if the graph that we have created so far contains that username, and if not, then we go ahead and add a node for it. So another example where our nodes represent users. Then we check to see if our nodes are connected already. If our current user is already connected to this other user via an edge, then we update the weight for that edge by saying these two users have been connected multiple times. So this weight gives us some information about how closely connected two users are. You don't have to include weights in a graph, but here this gives us some additional information. If there is no edge, though, that's the else statement here, then we go ahead and add an edge between these two users and set its weight equal to 1. So we'll run this and we'll see that we have about 6,000 to 7,000 users in our network. And for debugging purposes, we can print out some users who have weights that are higher than 1. And we see that Mansour Moraz, right here, referenced iTelly, or mentioned iTelly a couple of times. Stella Creasy mentioned Foreign Office a couple of times. But in general, we see relatively few accounts with high weights. So now that we have built our graph, the next thing to do is to look and see who are the most central users in our graph. So who gets retweeted the most, or who is being mentioned the most. There are different kinds of centrality that we could explore as well, so like closeness centrality and betweenness centrality. This little paragraph here describes the difference there. But for our purposes, we'll use the PageRank algorithm to figure out centrality or authoritativeness. So PageRank was originally introduced by Sergey Brin and Larry Page for an early version of Google's search. Now NetworkX has a nice implementation for this, where we can take a network and then apply the PageRank algorithm to figure out ranks for the different nodes in our graph. But the first thing we want to do is some processing. So we have about 7,000 users, but we don't necessarily need to process all 7,000. So for instance, users who haven't mentioned anyone probably aren't going to have very high rank because they're not connected to anybody. So what we want to do is go through 5 iterations where we remove nodes that have degree less than 2. So degree is another way of saying number of connections. So a node's degree is the number of connections it has. Now we go through this list and say we'll find all nodes in our graph whose degree is less than 2, so they're connected to less than 2 individuals. And if we don't have any nodes, then we just break out. We don't have any to delete. And then we go through and remove these nodes that have few connections. So a node that exists in only one connection or exists on its own, what's called an isolate, we'll delete those from the graph because we know they're going to have low page rank, and we know they're going to have low centrality. And we run this and we see that in our first round, we delete almost 6,000 users. And this makes sense because a lot of our users probably aren't mentioning other people. They're probably posting about thoughts and prayers. And in each additional round of pruning, we're going to remove fewer and fewer people. Now, why are we doing several rounds of pruning? Well, for one, if we deleted everyone with 0 degrees or 1 degree in the first round, then maybe we've left several accounts who now have no or few neighbors in the graph after doing that pruning. So we do this several times to make sure we have a nice stable graph where the remaining nodes are highly connected. So now we can run the PageRank algorithm against our graph. Now what this PageRank algorithm will return is a dictionary of usernames and their PageRanks. So we see that here with high rank nodes is going to be a sorted list of the keys from our PageRank dictionary, sorted by whatever their PageRank score is. And we'll go ahead and reverse them. So we have the highest ranking nodes first. We print those out and we see the conflicts account and the Aronheim account and the Brussels Airport account are the 3 most authoritative accounts in this network. And this makes sense. So we've seen the Aronheim account many times. This is the account that shared the video of people running away from the airport. The Brussels Airport account itself and the conflicts account sharing information about the event. So it makes sense that these are going to be the most central accounts in our network. Now we can actually plot out what these PageRank lists or what these PageRank scores are. And we see down here where this x-axis is the user number and the y-axis are the PageRanks. We see the vast majority, almost 250 of our accounts, have very low PageRank. And then we have about 100 accounts that have slightly higher PageRank. And then here at the end, we only have about 7 accounts that have any sort of higher or significantly higher PageRank value. So most of our accounts are not really central to this network. They're going to be on the periphery. So, and if we were looking at the Kevin Bacon network, these would be actors who are not associated with anyone. In our case, they're users who probably are not mentioned by other users very often. Whereas here we have several users who are highly influential or get lots of mentions in our network. So now we can visualize this graph. Now NetworkX is not the best solution for doing graph visualization. There are other packages for this like NodeXL or Gephi, but we won't get into those. In this case, we have the draw function for NetworkX that will try and place our nodes and edges in our graph in some sort of reasonable way. Now there are algorithms for this called layout algorithms. NetworkX provides several of them. We'll use Spring Layout just because it's easy. There's a more sophisticated one called Fruchterman-Reingold, or you can do random layouts. You can play around with this. But for our cases, we'll just use the Spring Layout. The draw function takes in a number of arguments for the actual graph, the layout mechanic that we just did, node colors, how wide our edges are going to be, are we going to include labels, and our node size. So for this, we'll just create a simple graph with no labels and a node size of 50, because what we want to do then is add labels only for our high-ranking nodes. So now we can go to our high-ranking nodes list. So these are the top 10 highest-ranking nodes by PageRank. We can get their scores from our PageRank values and normalize our PageRank scores based on whatever the min and max was from our score list. This HR values line here will go through all of our names of our top 10 highest ranking nodes and normalize them using this minimum max value. And then we can draw additional nodes, or draw over these nodes with our high ranking names. We'll make them larger in size and a different color based on whatever their score is. This CMap here is a color map that will scale color based on these values. And then we have these additional lines here that will add labels for these high-ranking nodes. We go ahead and run this, and we see this graph is presented here. It's not the most legible graph, but that's part of the issue with using NetworkX for visualization. If you go look at NetworkX's documentation, it tells you there are other solutions for this. Or for network visualization, it encourages you to use them, but this is at least a quick and easy way to visualize our network. So we see a couple of things that we've seen before, or a couple of accounts that we would expect. So here's the Arnhem account, the Brussels Airport account. We have Chris Sacre Blue. So these are all the accounts that we saw in the top 10 of our highest ranking nodes list, and the connections between them. So now we can look at community analysis. There are a bunch of nodes in this graph that make it kind of difficult to understand. So we can break this graph down into a collection of communities, and hopefully this will give us some better insight into how this network is constructed. So the NetworkX package includes an algorithm for doing community analysis. So we'll go ahead and import that. And we'll use the Girvan-Newman algorithm, like I mentioned, to look at communities here. Now, the Girvan-Newman algorithm is interesting in that it gives us a decomposition of community structure. So if we run it, we'll get this community iterator. Now, what's in this iterator is a collection of nested community structures. So the first element in this community iterator is the primary set of communities in the entire graph. And then subsequent items in the community iterator would be sub-nodes or subgraphs within these major communities. So we don't care about those subgraphs for now. For our purposes, we'll just look at the top level communities. So these are the largest, most basic communities in our network. So we'll run this. This will take a minute to run. And now what we want to do is visualize and try and characterize these top level communities. So to do that, I wrote several functions here that essentially do things that we've seen before. So this first one just draws a graph. So given the graph function or given the graph object that we have, we'll use this drawGraph function to create a quick visualization of this network. We have find author nodes, so this function here will use PageRank to find the most authoritative nodes for this graph. So we'll use this to characterize who are the central accounts in this particular community. For our purposes, we'll look just at five accounts, but you can change this to look at fewer or more. And then we'll characterize these networks based on hashtags as well. So we can look at what are the most shared hashtags in a particular community. So we'll run that cell. That cell just goes through and defines these functions. And then for each of the communities that exist in our top level communities, we will try and print out these characterizations or view these characterizations. But we'll skip small communities or communities with fewer than 10 users. We'll print out what community ID is and the number of users in that community. And then we'll use the subgraph function of the directed graph object that we have here to look at just the graph that contains the users in this particular community. From here we can find the authoritative nodes using our findAuthNodes function. We can find the most frequent hashtags, and then we can draw this graph. So here we have community 1 with top users Sky News, RussiaToday.com, Fox and Friends, and frequent hashtags for Brussels, Brussels Attack, Terror Monitor, Pray for Brussels, and this relatively sparse graph here. Whereas for Community 2, we have conflicts, Arnhem, Brussels Airport, BBC Breaking News, references to hashtags for Brussels, Belgium, Zaventem, Malbeek, Brussels, and Brussels Attack, and BRT News. And we see this one as a slightly more dense network as well. Whereas here in Community 8, we have top users for Plan2 and Euronet Plus and Unilad. So Plan2 is a journalist for Le Monde versus Euronet Plus, which is a radio station in the EU. And we have Pray for Brussels and Brussels Attack. So it seems that these kind of communities break down along language lines like we saw with the topics before, with EU coverage here in Community 8, BBC Breaking News, so it's probably English language coverage with Arnhem conflicts and BBC Breaking News. And then up here we have more coverage as well with Sky News, Saborka, and RT.com, and Fox and Friends. So this gives us some insight into the different organizations. What are these different organizations saying about the event? In this community we have references to terror, whereas here it's mostly references to the attack and information about the attack. And down here we have information about the attack as well. So that's it for Module 10. Now for the homework for this module, you need to take this notebook, update it with your event right here, and then run this analysis on your event data as well to figure out and identify the authoritative users or organizations and try and visualize the graph, and then break down your data along the different community lines of people who are discussing your event. As always, if you have any questions, feel free to reach out to me on Slack.